Hello and welcome to the 11th lecture in this series. So I'll continue with by giving some more examples of manifolds and move on to talking about smooth maps between manifolds. So let me start with the case of, so the fourth in my list. Last time I talked about, I ended with open subsets of manifolds. Now the fourth in this list would be a product manifold. So let M1, N1, M2, N2 be manifolds. Then let's look at, consider M equals M1 cross M2, N2. So consider this space. Well, to begin with, we have to put a topology on this, or if we regard this M1 and M2 as metric spaces, we have to put a metric. We can come up with a metric on this. Now, in terms of topology, this would be with the product topology. So recall that the product topology is its defining feature is that if you look at open subsets of the form U cross V, where U is an open subset of M1, V is an open subset of M2, then sets of the form U cross V forms a basis for the topology. So the main feature is that sets of this form U cross V, U open in M1, V open in M2 forms a basis for this topology. So that's all that one needs to know about the product topology. And so so this makes it a topological space. Now I want to define a manifold structure on this. So the definition of the product topology suggests that a chart on M1 cross M2 it's a reasonable thing to start with a chart U in M1, a chart V in M2, and look at the product. And of course one has to write down a suitable homeomorphism on that chart. So let's do that. So I'll start with an atlas on M1, U alpha, phi alpha, and V beta, C beta be atlases for M1 and M2 respectively. Consider U alpha cross V beta, and then I'll define this map phi alpha cross C beta, where the maps are defined as follows, where phi alpha cross C beta. Now this would be a mapping from U alpha cross V beta into Rn plus N1 plus N2. And this map is defined in a rather obvious way. So I'll take x comma y where x is a point in u alpha, y is a point in v beta, and just define it to be phi alpha x, c beta y. So this phi alpha x would be a point in Rn plus 1, Rn1, and c beta would be a point in Rn2. So this actually would be a point in Rn1 cross Rn2, which we naturally identify with Rn1 plus n2. Note that, so with this definition, note that the image of this map phi alpha cross c beta is just the image of phi alpha with the Cartesian product of this with the image of c beta. So it's quite clear that this is the case just by the way the map has been defined here. Just from this, one can see immediately that this equality holds. And the point of writing this down is that image of phi alpha is, so this is open in Rn1, this is open in Rn2. Therefore, the product, the Cartesian product of this open set with this would be an open subset of, therefore, image of phi alpha cross c beta is open in Rn1 plus n2. Since it's a Cartesian product of open subsets in R1 and Rn2, Rn1 and Rn2. Moreover, so one can easily check phi alpha cross c beta is a homeomorphism onto its image. So it's a continuous map and its inverse is continuous. And that follows immediately from the corresponding properties for phi alpha by itself and c beta by itself. Well, what about the transition functions? It's a bit messy to write down, but anyway, the formula is simple enough. So let's say we have, suppose, so as usual, one has to start with two charts which intersect on M1 cross M2. Suppose U alpha 1 and U alpha 1 cross V beta 1. This is one chart. Intersection U alpha 2 cross V beta 2 is not empty. This is the case where a transition function is even defined, and it's of course one has to write down the corresponding domain and so on, but the map itself is rather easy to write down. So the transition function can be checked to be equal to, so it is phi alpha 1, what I call phi alpha 1 times C beta 1 composed with phi alpha 2 times C beta 2, the whole thing inverse. And the way these maps are defined, it's just phi alpha 1 composed with phi alpha 2 inverse, comma, or rather let me just act it on a point x comma y. Now this time x and x comma y would be a point in Rn1 cross Rn2 rather than the manifold, since the domain of a transition function is an open subset of Euclidean space. So I have to start with x comma y here. This n2 did not come out properly, so let me write it like this. Rn, oops, maybe. Let me rewrite this. So this is Rn1 cross Rn2. So this is acting on x, and then similarly C beta 1 composed with C beta 2 inverse acting on y equal to this. Of course, so this x comma y, so I acted on x comma y, where x comma y belongs to, so strictly speaking it would belong to C alpha 2 cross C beta 2 of this intersection. Let's just give it some name. Let's suppose let's call it W. W equals this. So it is just then I can just write, oops, so x comma y belongs to this, which is an open subset of Rn1 cross Rn2. The point is that the way this charts and chart maps were defined, it's quite easy to see that the transition functions are smooth because they sort of get decoupled like this. The x part gets separated in the here, and the y part gets separated here, and each map individually is smooth. So therefore the transition maps are smooth, and that's that pretty much concludes the list of simple examples that we have. But already, even with this rather limited list, one can come up with some interesting manifolds. So for instance, since we know since S1 is a manifold, T2 which is defined to be S1 cross S1 that this is the two-dimensional torus. S1 cross S1 is a two manifold. So this S1 is a one manifold, so therefore this is a two manifold, a manifold of dimension 2. So this is the two-dimensional torus, which is actually, now normally one thinks of a torus as a surface of revolution in R3, but the way we have defined it, this T2 is actually a subset of S1 itself is a subset of R2. So this would be R2 cross R2, which is R4 rather than R3. So this description of the torus as a Cartesian product is as a subset of R4. Now, of course, one can prove that this is in some sense equivalent to the surface of revolution in R3. But we'll return back to that when we talk about submanifolds. Right now, the two-dimensional torus is a Cartesian product, and there's no reason to stop at 2. The n-dimensional torus defined to be the n-fold Cartesian product of S1. So, and this will give us an n-dimensional manifold. So, but one can get far more interesting examples and a huge selection of examples once I talk a bit about. First, I'll start with smooth manifolds, then tangent spaces, then turn my attention to submanifolds. Then we'll return back to more examples. So now let's now start talk a bit about smooth maps between manifolds. In fact, this is where, when we want to define a smooth map, this is where the reason for defining a smooth manifold in such a complicated way in terms of transition functions becomes clear. Why it becomes clear why one had to go through the business of looking at transition functions. So let's start with smooth maps between manifolds. So I start with let M and N be manifolds. As usual, the superscript denotes the dimension. And F from M to N map. Let us we want to say we want to talk about this such a map between two manifolds, talk about differentiability of such a map. The point is, the only notion of differentiability that we know until this point is differentiability of maps, Fréchet differentiability of maps between open sets in Euclidean spaces. So ideally one would like to reduce to the case of Euclidean spaces, and then using that one should be able to say that this F is smooth. Now the way manifold is defined, if you start with a point P in M, I know that it's going to be contained in a chart U phi phi. So let me call this U1. Similarly, this f of p is a point in the target manifold N. It is contained in a chart as well. So V and then a map C. So this is V1. So this U1 is an open subset of Rm, and this is an open subset of R. Like I said, one would like to reduce to the case of map between open subsets of Euclidean spaces, and then one already has a notion of smoothness and somehow use that to say something about F. So this picture provides a way of reducing to the case of open subsets of Rn. Namely, suppose I want to say that the map F is smooth at P. So I put it in some chart U, and I put f of p in some other chart, in some chart V. Then I get this phi, and this whole apparatus comes along with a chart. Now what I can do is I can look at phi inverse, start with phi inverse, then compose F, and then do C. So in other words, phi inverse compose with F, compose with C. Now we get what we want, since this is now a map between open subsets of Euclidean spaces. So it's natural to define, to say that F is smooth at P if this corresponding map that I have here is smooth at, well, P goes to some point here. Let's say this is Q equals phi of P. So if this corresponding map which I have here, I would like to say F is smooth if this map, the circle map, is smooth at Q. So in fact, let's make that definition. We say that F is smooth at P if for any chart U phi containing VC containing f of p, the map which I just wrote down there, which was well, I first did phi inverse, then F, then compose with C inverse, no, oops, not C inverse, the C. This map from U1 to V1. So these U1 and V1 are open subsets of Rn and Rm. The map is smooth at Q equals phi of P in 1. So this is the, yeah, so this now, right, so this is what our notion of smoothness. Now the main point is, as it turns out, this business of, here I wrote, for any chart containing P and any chart containing f of P, something should happen. Well, it might so happen that there are no charts. I mean, it should not be the case that for some chart, for a specific chart u phi containing p and a specific chart containing f of p, this condition might hold, that the corresponding map is smooth, but for some other chart it might not hold. One doesn't want that to arise. So in other words, one wants to just be able to check this condition for a, rather than any chart, one would like to replace any chart by some chart. In other words, it should be, if it this condition holds for one chart, then it should be the case that it holds for all charts. Why do we insist on that? Well, it's just that when we are talking about a smooth manifold, the charts themselves are not that important. Even though the definition involves a chart as an atlas, the atlas itself is not that important in the sense that it gives rise to a certain structure on M called, well, which I didn't emphasize, but it might so happen that I can replace this atlas by another atlas, which is in some sense equivalent to this. And when I do that, essentially all the corresponding notions will turn out to be the same. So the thing is, rather than emphasize charts, so whatever definition we make, ideally we would like to make them independent of charts. Here, for instance, of course I've used charts, but at least I should ensure that it should not depend on the specific chart. It should be, if it holds for one chart, it should hold for any other chart as well. That is one thing. And secondly, in any case, if one wants to check that a map is smooth, it will be quite hard to check this for every chart. Typically what one does is one chooses some nice chart and then checks various things. For instance, when dealing with the sphere, the stereographic projection gave rise to two nice charts where formulas were rather simple, and one would like to check something, for instance, a map on the sphere is smooth just by working with stereographic projection rather than some other chart. So for these two reasons, that one would like to, so one would like to replace any chart by, if it holds, i.e. if F is smooth in the above sense with respect to a pair of charts to a specific pair of charts, then F should be smooth with respect to any pair of charts. And in fact, that turns out to be the case. So the fact that this holds is precisely where one needs the transition function smoothness condition. So let me sort of illustrate why this is the case. So let's start with the point P. So this is my point P. And then let me call this as, so I changed notation slightly now. Earlier U1 was an open subset of R1, R some Euclidean space, but now I'll use U and U1 to denote two charts on M. And the corresponding homeomorphisms, phi, phi1. So this will land up in some x, x1. So both of these are now these both inside are M. And then on the other side, so F is my map, and then on the other side I have V. So this is V. And then here, this point is f of P. And then I have maps C, then C1, W, W1. So these two are open sets in Rn. Well, so let me stop at this stage, and then next time I'll continue with this picture that I have, and clearly sort of go into details about where exactly the transition function condition plays a role. So let's stop here. Thank you.